Good afternoon to everybody. This is our seventh lecture in the introduction to the geographical information system. In the first part, I'm just give you very brief information about today's lecture. Today's lecture, as I said before, it is about the geographical coordinate system, or let's say coordinate system and projection. I'm going to tell you why these are important and why we need it. Just emphasize once more, if you remember from the beginning of the lecture, I told you that GIS works with spatial data and descriptive data or attribute data. Last course, we just explained about the descriptive or attribute data, how we are able to store them as a database or under the database, and how we are able to work with them, how we could select them, how we could, let's say, work with those data, or how we are able to generate some new data such as, let's say, population densities, such as let's say area calculation, and etc. But this lecture right now we are going to work on the other part of the GIS, which is spatial data and mainly projection and coordination. If you remember from beginning, I told you that we have a main three entity: point, line or polyline, and at the end polygon. So we need to address to this entity, to this spatial entity, with use of the geographical coordinate system. Now, what is a geographical coordinate system, or maybe later you will see it as a GCS? This GCS uses a three-dimensional sphere surface, as definitely you know, which is actually refer to the center of the Earth with use of latitude, longitude, definitely by the angles to the center, and of course if we have a distance from the Earth, our latitude also our altitude also increase accordingly. As you can see, we are able to address to any point on the Earth through this latitude and longitude from the corner of the Earth. So as you can see right now here, the longitude or equator, which is the 0, 1, then it is increased to north and south by 90, let's say, a slice, or 90 line. And we have a latitude, which is passing the main one, the 0, 1 from the Greenwich and in the London. So the rest is slice the Earth, let's say, into the, let's call it vertical dimension, from west to east. They start to cut the Earth. So now, from this part, since I'm just explained for you what is a geographical coordination system, we need to emphasize in something else also. For every continent, you know that the Earth, our Earth, is not like an ellipse, or is not have a specific shape at all. Imagine this right now. This let's just have my pointer. This red, let's say, sorry, this blue one, this dark blue shape, it's our Earth surface or geoid. You see, it is not have a specific shape. Sometimes it is going to up, like the hilly side. Sometimes it is going down, maybe inside the valley or in the sea or ocean, or within a mountain. Again, it's climbed up. So it doesn't have any specific shape. And this is make our job difficult to, let's say, addressing any point in this geoid or earth surface. That's why we start to use a datum. Okay, what is a datum? Datum actually it is look like a imaginary ellipse or sometimes circle, let's say. We just try to put it in a specific part of the earth according to our, let's say, work purpose. So for each area according to the ellipse, according to the, let's say, geoid of that region, we will draw some ellipse and we call it as a datum. For instance, in America, they decide to use North America datum, let's say for region 27. So let's say this green one is somehow fit for this part, as you are able to see. But let's say I try to also draw one other. Let's get this black color. Imagine we want to work in this region. Accordingly, I need to draw my own datum with use of another ellipse, which is better fit for this area. You see, this is now better fit for this region or this area that I am just right now drawing with orange. But we have one global one. We have one global datum, which is this red one, this dark red one. We call it World Geodetic System 84, which is defined by 84 in 1984. So this is fit for entire world, but for a specific job, for a specific place, we should use a local one. Otherwise, we will face with a different problem that I'm going to show you by coming a slide. But for a normal research, let's say just a geographical research, it is fine. It use this one. But for a specific job, such as a field survey, such as a cadastral drawing, and this sort of job, we are not able to use that one. For you also be aware, as an architecture, you need to use a local one because you are dealing with a land. And if you have a distortion in land, you will face with a problem. I'm going to explain more detail, but just very briefly, imagine this is our origin right now, and we use two different datum A and datum B. Same place on the earth, same place, we put two same place on the earth. Look at this red one. With one datum, the address is equal to 244,249. But again, same place with use of other datum, the address is changed, which is 208 and 309. So this is the distortion that right now I'm going to talk about it. But before going to that part, I want to also take your attention to the projection. What is a projection? Maybe you are mainly in a primary school, or I don't know, in the middle school. You see definitely this, that your teacher or instructor asks you to project the orange peel into the surface. So you are able to cut with a specific cut, as you can see here. You are able to project the orange onto the surface. Definitely with if increase your cut, your projection become too much smooth and better. Okay, so it means that you need to cut actually orange peel to the small piece, okay, in order to have a less stretch or distortion. This is same for earth. If we want to, because we are working on the paper, we are not working on the sphere, so that's why we need to, let's say, sphere the earth surface onto the, let's say, flat piece. Imagine a very, very big flat paper. So for this, we have a different projection method. One of them, as you can see, this is a simple cut. And as I told you, if we increase the cut, we decrease the distortion. There are different projection. For instance, look at to this Mercator, the first picture on the top. You will see that the equator region, actually here, doesn't have much distortion. But when we go towards the poles, north or south, you will see the distortion problem. For instance, here, look at just Greenland. It's almost as big as Africa continent, which is definitely not. Or look at to the South America size, how it is become change, or even north part of the Russian. So this is the problem of the distortion when we are talking about the distortion. But when they use other one, for instance, good homologine projection, which is look like the orange peel, if you start to cut this part, this, let's say, white part, and start to stick those edges together, you will again have your earth as a sphere and one sphere again. Okay, so you see right now how Greenland look, how small, is not anymore as big as the entire Africa. This is about the projection problem. So we have other projection. For instance, as you remember, I told you, if we increase our cut, into the very, very small part, so our distortion become less and less. But later, we have a difficulty from recognition by our mental. You see, now it is a bit difficult for everyone to imagine these. For instance, where is the Austria? It's somewhere there. However, we always saw this map, this project map, similar to this first one, like a Mercator project. We can easily imagine it. But right now it is very difficult to imagine. But look at this one, how accurate. For instance, look at right now the Greenland size. It is become a very, very small in comparison to the Africa or even Austria. But if you go there, it is very big, even bigger than Austria, okay, which is wrong. However, if you're looking here, it has become very small, but here also it's look like different. So this is about the projection. So if you want to map or only a proportion of the Earth's surface, there are projections that are better suit for a specific point of the Earth according to your study purpose. But we are able to use the global one. But for, as I said, for a specific job like civil engineering, field survey, architecture, we prefer to use more accurate and more suitable or better one according to our area. Now come back to the map projection. I told you that I'm going to tell you what could be a possible problem when we have a distortion. Now look at to this curve line, or this, let's say, I1. Okay, imagine this is our Earth. Okay, we consider it as an Earth, or we consider it as a, let's say, geoid or ellipsoid surface. Now let's take your attention to something else here. Let's take my pen. Imagine you have a piece of property in this location, from here, from capital D to capital E. Imagine you have a property here. You have a land. Okay, you have, let's say, 100 square meter land in this area. And this line, let's also change the color. And this line, this, try to go over it. I don't have a tablet and pen. I try to draw it with the mouse. So if this red color is our paper, okay, if this red color, our map surface or paper, after projection, my property, if I said it is 100 meter, this time, let's say, become 200 meter. Which is wrong. Okay, in a reality you have 100, but after projection, you will see that you have a 200. Now imagine as an architecture, so in a map, you have a land of 200 meter square, and you are start to design your project accordingly. Since you have a 200 square meter, so you start to make a very big house on top of it. But when you go to the reality, to the ground, when you want to build it, you will see, oh, my design is not fit there even. Instead of, let's say, design 3+1, I supposed to design a studio, very small studio for that land. So this is the one big problem. Now let's give another example. Let's come to the another example. Imagine here also you have a piece of land in this distance. This is real Earth. Between A and B, you have a piece of land, let's say 500 square meter. But after we, let's say, project it into the paper, it's become this much. Let's say before was 400, now become 300 square meter. Same things happen to you. It means that in reality you have a big land, but in the paper your map looked like very small. What happened to your property? What happened to your land price? It seems that you lost almost half of your property. So these are important, and when you are dealing with a projection. Accordingly, how we are able to solve, you remember that I told you if we cut it into a small piece, we solve this problem. What does that mean? Instead of having one big red, let's say, paper, we should have many small green, let's say, paper for each area. in order to minimize this problem. Okay, instead of one big, let's say, red paper, actually I'm call it as a red paper. Of course, it is not a red paper, it is a projection, like this surface. So accordingly, we have a different sort of the projection, but the most popular one is a cylindrical, conical, and azimuthal. Okay, mainly in this course, we use a cylindrical. Okay, that's why I'm going to emphasize on it. I'm not going to too much detail and deep, but this itself, this part itself is one course in a geoscience and geology and field survey. Now, I tell you we are going to use a cylindrical. We put a imaginary cylinder, we call it transverse, okay, and we fit it into our sphere. And then we start to, let's say, expand our cylinder. After that, we will have a 60 different transfer Mercator. Okay, as you can see from region 1 here, we will start and then go to the 60. We have a 60 different region of the Mercator. Okay, we call it UTM or Universal Transfer Mercator. And we have a two part, north part and a south part. For instance, if we work in, I don't know, let's say we are working in a California, okay, I think it should be somewhere here. So for that purpose, our coordinate become WGS 84 UTM zone 10 or 11, okay, and north, which is in a north part. Or again, for our purpose here, for instance, we want to work in a Cyprus. A Cyprus is almost here. If we go up, it is 36. So since it is in a north part, it is become 36N. And vice versa, if I'm coming, let's say I'm working here in a Sydney. Imagine here is a Sydney, so my projection or my coordinate become 55, of course, in a south part. We have other projection methods such as Lambert and Albert. I'm not going to deal with that. But we have a one null island here, as you can see, 0, 0. Okay. This null island, it is almost located in a Gulf of the Guyana in the west part of the Africa, where the primary meridian and Ecuador meet each other. So there is a buoy on there, which is consider those location. That location have a 0 latitude, 0 longitude, and since it is in a mean sea level or MSL, the altitude of it also equal to 0. If you are in an architectural drawing, definitely you will saw that you have a contour line. In a front of one of contour, you write that MSL equal to, I don't know, let's say 50. It means that according to mean sea level, this contour line have a 50-meter height from the sea. And then you say this one equal to 0 in my drawing. And then you start to work accordingly with that one. This is about null island, this is about the projection, and this is about the coordinate that I want to give you in this, let's say, lecture.